So today is the last data mining techniques we're going to learn. It is the association rules. So association rules is a little bit different with clustering or classification because this techniques is specific to, let's say, to get or to understand the rules inside the data. So when we talk about rules, it means it is the relationship between items in the data set. So we talk about the association rules. So we here now talking about the correlation between items in the data set. Mostly these algorithms is used for analyzing market basket transactions. For example, this is the most basic one. Let's say we have 5 transactions. Let's say in the store, they sell bread, milk, diapers, beer, eggs, what else? Coke. Yeah, they have 5 items, 5 different items. Okay, and then for each data, so the data points in association rules. First, the difference is the data point here. Each data point will consist of a list of items. Like this, the first transaction, let's say the first transactions, it is a list of the transaction, it is a list of items both in transaction 1. So the first transaction, he or she buy bread and milk. And then the next transactions, it is also a list of items buy both in the transaction 2. So they have, like, for example, bread, diaper, beer, and eggs. Okay, so for the association rules, we're going to find out what is the correlation or rules between items in this transaction set. Okay, for example, the final result of the association rules will be, for example, if someone or the customer buy diaper, then he also will buy beer, for example. Or if the customer buy milk and bread, then he also will buy eggs and Coke. Or beer and bread, they will also buy milk. So this is the if, then this is then. If you are more familiar, if buy this, then they will buy the next one after this row. Okay. Of course, to find out these rules, we have to do some steps, and these algorithms called the association rules. We have many algorithms left. Okay. This one, for example, before we talking about the algorithm, first we have to know some definition used in association rules. The first one is ITEMSET. So ITEMSET is a collection of it can be one or more items. For example, here, this is the total transaction. Let's say we have 5 transactions. We have several items. Then from these several items, we can create item set. Of course, we have K item sets, means that K refers to how many items in the set. For example, we have 1 item set. Then here, the element of the set is only one item. So for example, we have bread, we have milk, and each of these, all of this, we have beer, we have diapers, and also all items. Of course, consists of 1 element. Then we also will have two item set. Two item sets means there are two items in one set. It can be bread and milk, or bread and diaper, bread and beer. So each pairs of these items. Uh, we also can have 3, 4, 5. Of course, the biggest K is equal to the number of items. If we have, for example, 1, 2, 3, 4, 5, 6, bread, milk, paper. Yeah, okay, we have 6. For example, in this case, we have 6 items. So the biggest item set for this case, K is equal to 6. So 6 item set. Of course, we cannot make 7 item set because the maximum item is 6. Okay. And then we will have what we call it support count. So support count means that it is the frequency of the occurrence of an item set. For example, we have this one. For one item set, we have bread. So we will calculate how many bread appear in the transaction. For example, this is 1, 2, 3, 4. So here, for item set bread, the support count will be 4. How about, for example, milk and beer? So we find how many transactions includes milk and beer. So we see this is only milk, this is only beer. Or this one, the third one, milk and beer. So 1, and the fourth one also milk and beer 2, and okay, only 2. So support count for a 2 item set milk beer is 2. Also for this one, for example, milk beer diaper. We see in the transaction how many transactions include milk, bread, and diaper. So milk, beer, diaper 1, milk, beer, diaper 2, milk. Okay, only 2. Yeah. So support count is this frequency. Besides support count, we have support. So the support count is the support is support count divided by the total transaction, or they call it fraction of transaction that contains an item set. Okay. Then we will have frequent item set. Okay. We have at the first time we have item set. So between all among all of item set that we have, there will be some frequent item set. So what is frequent item set? Frequent item set is the item set which has the support count, or the support greater or equal to minimum support threshold. So what is minimum support? So minimum support is a threshold that we set subjectively to determine how to differentiate. Oh, this item set is frequent. This item set is not frequent. For example, we set the minimum support is 0.5. Let's say 0.5. So for each item set, we will count the support, and if their support is greater or equal to minimum support is, then we call it frequent item set. Okay, or it means it represents transactions that occur very frequent. Yeah. Okay, and we will have association rule finally. So association rules is an implication expression in the form of if X, then Y. So of course, X and Y These two, they are the item set. It can be one item, any k item set. Yeah, for example, like this. So this one will be X, this one will be Y. Okay. The meaning or how to read these rules is if they have X, then we will have also Y. Okay. Rules evaluation matrix. This is the basic matrix. Okay. First, we have support that we just discussed here. So support if the fraction transaction that contains both X and Y. So for example, support is this one, the support count. This is the support count. Support count. This one is the total transaction. Total transaction. Okay. So for example, we have rules. This one, if customer buy milk and diaper, he also will buy beer. So how to calculate support? Support is support count divided by total transaction. So first we have to calculate this one. Okay, the first support count, the support count here belongs to support count of item sets contains these three. So not only X, but also X and Y. Okay, so here, don't forget support. Support is the count of item set contain X and Y. Okay, so here we calculate milk, diaper, and beer. Milk, diaper, beer 1, milk, diaper, beer 2. Okay, so that's why we have 2 here. And divided by total transaction, we have 5 total transactions, so 2 over 5, 0.4. Okay. And we also have confidence. Confidence is a measures how often items in Y appear in transaction that contains X. So how confident we are with the rules that we have. Okay, for example, this is the rules still using milk diaper. If customer buy milk diaper, then he will also buy beer. Confidence. The confidence is the support count. Support count of X and Y divided by support count of X only. Yeah. So here in our example, support count of X and Y. So support count of milk and diaper. Milk, diaper, and beer. We have 2, we calculated before. And then support count only for X. X means only milk and diaper. So we calculate milk diaper 1, 2, 1, milk diaper 2, milk diaper 3. So we have 3 here, around 0.67. Of course, higher confidence means that we are more confident that these rules will apply. We are more confident with these rules. Okay. Maximum value is 1. So confidence, the score for confidence is between 0 and 1. Support also between 0 and 1. The higher one is better one. We prefer the higher support or higher confidence. Okay. Wait. Later, if you try this, we also have to consider like the support or confidence is this one, or especially confidence. The confidence is divided by support count of X. So sometimes there's one rule, there will be some rules that have a very low confidence. So in that case, the reason may be because the item set X is very rare to happen. So it very infrequent. So for example, because the item set beer in this case, for example, sorry, milk and diaper is very only few transactions. So that's why um, these these rules can have a very low confidence. So we also have to make sure that the items that we want to understand the rules. For example, we have to make sure that items is included in many transactions in our data set. Or sometimes, for example, we have 100 items. We have 100 transaction. Okay. But in our case, let's say from 100 transaction, we have, let's say, 500 items. Oops, items. So in this case, a variation of the transaction will be so high. So in that case, you have to be careful because maybe it's very difficult to find rules with a high support or high confidence. Because in that case, maybe we need more data for the transaction. Because the variety items in the transaction is very high. So the count for the support or count for this one for the eggs will be very low. So it makes the confidence and support is very low. So the rules cannot be constructed. Yeah. So in this case, if we want to apply association rules, we have also to make sure that our transactions, number of transactions and number of items is quite balanced. So for example, we have 500 items, but we only have 100 transactions. So it will be very difficult to get the rules. Okay. In association rules mining test, for example, we have a given transaction T. T is a set of transactions, and the goal is to find all rules which has support greater than or equal to minimum support and confidence also greater than minimum confidence. Again, minimum support and minimum confidence is two parameters that we decided. As the decision maker. Okay. How to generate the rules? So the main task in association rule is generating rule. Okay. There are many approaches to generate rules. Okay. For example, the very basic one is a brute force approach. In this approach, of course, this approach will list all possible association rules. Then they will compute support and confidence for each rule, and they will eliminate rules less than minimum support and minimum confidence. So let's say we have only 3 items, A, B, C. Okay. So here in brute approach, brute force, they will list all possible association rule. It can be if A, then B, C, if B, then A, C, C, then A, B, then if A, B, then C, and all of possible combination of item that can make rules. Okay. They will list all rules, and then they will calculate support and confidence. So this is the rules, and they will calculate support, and they also will calculate confidence for each of these. Then they will eliminate rules with less than minimum support and minimum confidence. Let's say the minimum support is 0.7, minimum confidence is 0.8, for example. So, for example, we have this one rule, 0.5, 0.4. So then we eliminate this rule. We only keep rules that support, let's say the support is 0.5, 0.5. So we only keep support, we only keep rules which has a support and confidence higher than minimum support and minimum confidence. So this one we keep. Okay. If we only have a small number of items, brute force approach still can be applied. But you can imagine if we have so many items, then of course this approach will be very computationally prohibitive. So so many things we have to calculate. Yeah, so takes so much time, which is inefficient way. Yeah, this for example. This is the, if we have D number of items, then there will be 2 power of D number of items set, and of course they will be like, okay, this is the equation, they have the formula already. So if we have only 6 items, then they are around 600 rows that can be generated for 6 items. So the computational will be very inefficient. Okay, so that's why. Okay, that's why they will. We have more algorithm. We have to learn other algorithms, so it has more efficient way to get the rules. Okay. Okay. Okay, this is the example of the rules. You can calculate. For example, this is milk and diaper. We calculated before. Milk, beer, diaper. So here the support is milk, beer, and diaper. We calculate the support count of milk, beer, and diaper divided by total transaction 5. Okay, so we calculate milk, beer, diaper. We have how many milk, beer, diaper? 3, yeah. Milk, beer, 3 divided by 5. Okay. Milk, beer, diaper, milk, beer, diaper. Okay, 3. No. Milk, beer, diaper, milk, beer, diaper. Only 2, sorry. 2, 5. Yeah, so if you see here, these rules, they have the same support. Okay, because why they have the same support? Because they basically, although they have different rules, but basically these all rules generate from the same 3 item set. So the main item set is milk, diaper, beer. Okay, that's why the support count or the support, they have the same support. But the difference is the confidence. Okay, because the confidence is divided by support count of the only X. Yeah, so that we can have different one. Okay. Here, rules originating from the, yeah.
For example, for milk, beer, and diaper, for the confidence, we get the sum of items with milk and beer divided by the sum of milk.
You mean the first one?
The second one, milk,
the second
beer.
One.
Yeah.
Okay, so we calculate confidence or support?
Confidence.
Okay, confidence. So for the confidence, we will calculate a count of milk, beer, diaper divided by count of milk and beer. So
okay. Thank you.
We have milk, beer, diaper is 2, milk, beer 1, 2, 1, 2. So we have 2. That's why equal to 1.
Thank you, Dr. Farah.
You're welcome. So here we remember that rules originating from the set from the same item set. So like this, all of is from the same item set have identical support, but they can have different confidence. Okay. We may decouple, that's why we may decouple the support and confidence requirements. Okay. Okay, so we know the brute force approach is very inefficient. So they are basically, there are many algorithms for mining association rules. They focus on how to generate the frequent item set and how to generate rules efficiently. Yeah, so in the brute force, we list all the rules and then we calculate support and the confidence, which is takes so much time. Although it's very simple, but it takes so much time and too many combinations from the item. Okay, so in association rule, the algorithm will focus on these two main tasks: generate frequent item set generation and rule generation. So mostly they will, different algorithm will have a different way to do these two process. Okay. Basically, frequent item set generations is a process to generate item set which has support greater than minimum support, or it should be not generate, but it's fine to find all item sets the support is greater than minimum support. And also for the rules, after we find the frequent item set, and then we generate the rules. So why we have to find the frequent item set first? Because rules from infrequent item set, of course, the confidence, the support and the support and confidence will be less than minimum support or minimum confidence. So at the end, we will not use this. Yeah. So that's why at the first step, we focus on what is the frequent item set. So the rules that will be available for us is the rules generated from frequent item set, only from frequent item set. So we don't need to spend so much time to generate rules from infrequent item set. Okay, so after we have the frequent item set, then of course from items in the frequent item set, we can find out the combination to get the rules. This one, generate high confidence rules from each frequent item set. Of course, each rule is a binary partitioning of the frequent item set. So for example, A, B, C is the frequent item set. Binary partitioning mean that sorry, we can have A, B, C, or A, B, C. So we have binary frequent partitioning. We have to partition. We have to divide items in the frequent item set into X and Y. So which one is X? Which one is Y? Because the rules is if we buy X, then we also will buy Y. Okay. Okay. This is the main idea. Focus on frequent item set. But again, generating frequent item set is sometimes also computationally expensive. Yeah. Still computationally expensive. Okay. So let's say, for example, we have A, B, C, D items. We have 5 items. So all of these is the item sets, possible item sets, okay, or they call it candidate item sets. Brute force approach to find out the frequent item set. This is the approach. For example, each item set is the lattice is in the lattice is a candidate of frequent item set. So they have the list of candidates first, and then they will calculate the count support of each list here. Okay, and this one still expensive because this is a brute force approach. Okay, so what can we do to minimize the computational time? For example, we can reduce number of candidates. Okay, if the complete search is the brute force, so list all possible combination like this, list all of this. Yeah. Oops. Okay. But then we can reduce number of candidates by use pruning techniques. Later we will discuss what is a pruning techniques to reduce the number of candidates. Okay. We also can reduce number of transactions. Okay. Because reduce size of n as the size of an item set increase. Okay. We usually this reduce number of transaction is used by this kind of algorithm, the HP or vertical based mining algorithms. So these two algorithms, they are the algorithms for association rules, which consider this idea. Okay. For this pruning is using usually a priori or FP group. Okay. We also can reduce number of comparison, N, M. Okay. N is number of candidates. Sorry, yeah. N is number of transaction, M is number of candidates. Okay. This one use efficient data structure to store the candidates of transactions. So we don't need to match every candidate. Okay. Okay. Reducing number of candidates, the first techniques. How to reduce number of candidates? We have what we call it a priori principle. So this is a basic principle in association rules. They call it a priori. So the idea is if an item set is frequent, then all of its subset must also be frequent. So for example, we have 3 item set. Let's say A, B, C. If A, B, C is a frequent item set, then all subset from this, it can be A, B, C, A, B, A, C, B, C. All of these also frequent. Okay. Yeah, this one. A priori principle holds due to the property of the support measures. Yeah, this is mathematically speaking. Yeah. Okay. Support of an item set never exceeds the support of its subset, of course. So here, let's say support of item set, support here, support count. Yeah. Let's say if we're using support count, make it simple. Support count of ABC here. If, for example, if this is 10, then this one maximum is 10, maximum of each of these, yeah, because support of item set never exceed the support of its subset. Okay, that's why if only 10 we say it is frequent, then of course ABCD or all of the subset is also frequent because they have, of course, the count for this will not be less than this one. Okay, this is known as anti-monotone property of the support. Okay, so this one, for example, if AB is Okay, we reverse the theory. If AB is infrequent means the count support or the support is less than minimum support. Yeah, infrequent. Then all of the superset, because this is, we call it this is superset, is also infrequent. So we can prune this. We don't need to consider all of this superset because AB is already infrequent. So any item set construct from IB will be also infrequent. So we can eliminate all of this. We don't need to consider this. Okay. In this case, we can save some time to analyze this infrequent. Okay. So here, the step of a priori letter, we start from the one item set, A, B, C, D, E, for example. Then, for example, oh, A still greater than minimum support, so still frequent. Then from A, we construct a two item set, A, B, AC, AD, AE, for example. Then for each of these, we calculate the support. But then we found out, oh, AB, the support is less than minimum support. So we don't need to further extend this AB. Focus on other item set which is frequent. For example, AC, oh, AC is frequent. So, okay, we can continue develop the next three item set using AC. For example, ACD, ACE, for example. Yeah. But for example, we then find out, oh, DE is infrequent. So from here we see if DE is infrequent, so we don't need to consider this one, this one, this one. Also, we don't have to calculate this one and this one. Yeah, because DE find out it is infrequent. So here, see, we can eliminate some possible item set, so we can save sometimes. Okay. Oops. Yeah, for example, like this. This is still the list of transactions. Okay. First, we start from the one item set. Okay. One item set. So here we have all each item is, and of course we will count each frequent support count. This is the support count. Okay, for bread, 1, 2, 3, 4. That's why we have 4. How about Coke? Coke, we have 1, 2. So we have 2. And then milk, 1, 2, 3, 4. 4. We calculate for each of these: beer, diapers, and egg. Egg, egg only 1. Okay, here. So, and for example, this is we set minimum support is 3. Support count is 3. So, because the minimum support is 3, so any item set, one item set, because we still have one item set, if the support count is less than 3, we can eliminate. So this one we eliminate, this one we eliminate. We only focus the item set which has a count 3 or greater than 3. Finally, we have bread, milk, beer, and diaper. Okay. Then after we have one item set, we continue to two item set. Okay. So here we pairs two item set. Of course, the two item set is from, because we use a priori principle, so we focus on combining for two item set, combine from one item set, but no need to consider infrequent. Okay, so for example, we have bread and milk, so we combine bread and milk here. Then we also combine bread and beer, second one. And then bread and diaper, bread diaper. Then we also have milk and beer, so this one. Milk and diaper, this one. And finally, beer and diaper, beer and diaper. Yeah. So here, no need to involve quote and X because it is these two are infrequent. Okay, then after we have two item set, this is two item set, we will calculate the support count for the two item set. Okay, so here we calculate bread and milk. We calculate bread and milk. 1, 2, 3. Okay, we have 3. This is from transaction 1. I put here 1, 4, 5. This is the transaction. And bread, beer and bread from transaction 2, beer and bread 4. Okay, only 2. So 2. Bread and diaper. Let's see, bread and diaper. 1. No. Bread diaper. Oh, this is transaction 4 and transaction 5. Why only? Bread and diaper. Oh, sorry, 2, 4, and 5. This one. Bread diaper, bread diaper, bread diaper. Beer milk from transaction 3. Beer milk 4, 3, and 4. Diaper and milk. Let's see. Diaper and milk is 1, transaction 3. Diaper transaction 4, transaction 5. 3, 4, 5. So that's why they have 3 support count. Beer and diaper. Beer diaper. Well, which one? This one. Transaction 2, 3, 4. Okay, 2, 3, 4. Okay, so this is the support count for each item set. 3, 2, 3, 2, 3, 3. Okay. Again, here, before we continue to construct 3 items set, yeah, we can eliminate item set. We can eliminate infrequent item set. So here we know which one is have the minimum the support count less than minimum support. So here we can eliminate beer milk. Also we can eliminate. Yeah, so we can generate 3 item set only from frequent 2 item set. Okay. Continue.
Dr. Farah?
Yeah.
The minimum support would be based from the previous one, or should it be computed to a new minimum support?
For one case, the minimum support is always the same.
Oh, so it's the first one, right?
Yeah, still continue. Please.
Okay, thank you.
You're welcome. Okay. So now we construct the 3 item set. 3 item set from beer, milk, and bread, milk, and bread diaper. So if we combine these 2, it will be bread, milk, and diaper. Bread, milk, and diaper. This one. Bread, milk, diaper. And if we combine the first one and the for one, bread, milk, diaper. Bread, why again? Bread, milk, diaper. Bread, milk. Okay, bread, milk, diaper, still this. We combine this one and the last one, bread, milk, beer, and diaper. Okay, here we have, let's see, we have bread, milk, and we have beer and diaper. So if we combine these two, then we can have 1, 2, 3, bread, milk, beer. Which one? Bread, milk, beer. But we also can have bread, milk, diaper. Bread, milk, diaper. Oh, okay, here. And what else? Bread, beer, diaper. This one, bread, beer, diaper. And we also can milk, beer, diaper. Milk, beer, diaper. This one. Yeah. So make sure if we generate a higher item set, superset of the item set, then we have to make sure that all combination is already included in this item set. Okay. Don't miss one of them. Okay. Then again, we calculate the support count. So let's see, beer, diaper, milk. Beer, diaper, milk. Oh, this one, transaction 3. And beer, diaper, milk, transaction 4. And then beer, bread, diaper. Beer, bread, diaper, this one, transaction 2. Beer, bread, diaper, transaction 4. Bread, diaper, milk. Bread, diaper, bread, diaper, milk 1. Transaction 4 and 5. Beer, bread, milk. Beer, 4 and only 4. Okay. So this one, because all of this, all of this is less than minimum support, so we can stop. No need to calculate. Sorry, no need to calculate the 4 item set until we actually, because we have 6 item, we can generate into 6 item sets. But let's see, until the 3 item set, none of this is a frequent item set because each of this less than minimum support. So we can stop until 2 item set because further than this, there will no frequent item set. Okay, so all rules generated from all of this, I mean from 3 item set, 4 and 6, the rules will be not interesting because this confidence is lower than minimum confidence. Okay, so here we focus on, we stop, for this case, we stop until this 2 item set and focus on frequent item set, bread, milk, bread, diaper, milk, diaper, and beer, diaper. Okay. Yeah. This is the illustration of the a priori principle. We can do this manually, of course. We are smarter than computer, but this is for the computers. This is the algorithms. Of course, the computer should have a fixed step by step. Yeah. So this one, the formal algorithm for a priori algorithms. Okay. So let's say we have FK. FK refers to frequent K item set. So it can be F1 is 1 item set, F2 is 2 item set. Yeah. Okay. LK is candidate of K item set. Okay. So here we start from 1 at K equal to 1. So we start from one item set, and to generate F1, this one is like this. We generate candidate generation first, and then pruning candidate if the subset of K is infrequent. And then we calculate support, and then we eliminate the candidates if it is infrequent. So this is actually the formal definition of the step that we just discussed in the previous slides, like this. Okay. Candidate generations. Okay. In candidate generations, we can use a brute force method for candidate generation. For example, if we want to generate 3 item set, then the brute force, they will consider all item set, and then they have all of these candidates, and then they will calculate the count of supports, and then they will have the candidate for pruning. Means that the frequent item set, candidate of pruning is from all of these. They will see from the subset. Let's say because this is 3 item set, they will see from the 2 item set. If inside the items, the element is not included in the frequent 2 item set, then they will belongs to the candidate for pruning, candidate to eliminate. Okay. And another way to candidate generations, so for brute force, they just combine all of the item set. But for merge fk minus 1 and f1 item set, this is another approach. Okay, for the another approach is they will combine. For example, we will generate 3 item set. So k is equal to 3 here. So here we will to generate 3 item set, we will combine k minus 1. K minus 1, so in this case is 2 with 1 item set. So like this. Of course, this is a frequent and frequent. So candidate generation is beer diapers, and if combined by beer, then of course we skip beer diapers and bread. Beer diapers, this one we can skip because it's the same. Beer diapers and milk. Okay. And then beer diapers and diaper and bread. Yeah, we combine all of this, each of these, to get the 3 item set. And then after this, of course, we calculate the count, support count, and we will find out the candidate for pruning. Okay. We also can use this one, combination of fk minus 1 and fk minus 1. Okay, so if you ask me what is this method used for, if you remember, when we want to generate 3 item set, we have to find out all combination of this frequent, the 2 item set. Yeah, to generate this 3 item set, we have to think about how to get this 3 item set. So computer for this one, candidate generation, they can use brute force, merger like this, 2 and 1, or like this, k minus 1 and k minus 1. Okay. So k minus 1 and k minus 1, it means that, for example, if we want to generate 4 item set from, of course, the k is 4. So we will combine to get the 4 item set. We will combine K equal to, sorry, F3, K minus 1. So we will combine 3 item set and 3 item set. So for example, this is the 3 item set, ABC, ABD, and until CDE. To combine all of these, yeah, we will find out to see three item sets, but the first 2 item has the same items. Okay, for example, we will merge A, B, C, and A, B, D. So we'll have A, B, and then the last 2, C and D, A, B, C, D. Okay. We also can combine this one, A, B, A, B, A, B, A, B, C, and A, B, D. A, B, E, sorry. So we'll have A, B, C, E. Okay. And then we also can combine ABD and ABE. So we'll have ABDE. What else? Nothing more. Yeah. So we don't need to think about like, is it should we combine ACD and BCD? Should we combine this? Okay. So in this method, the first 2 items A, C, B, C, D, the first 2 items, they are different. So we don't need to consider combining these 2. Why? Because if we combine these 2, the result will be A, B, C, D. Is already the same with this one, A, B, C, D. Yeah. So here, let's say this is the methodology to generate the item set, but we know because the item set, if we combine all of this, make the computer combine all of this, each of them, it will be computational time expensive or same like before. Yeah, so these methods to eliminate necessary combination. Yeah, so here they will find out if we want to generate K item set, they will combine 2 item sets, means that from K minus 1 item set and K minus 1 item set. We combine this. Yeah, but again, how to combine is they try to find out which 2 letters or the first K minus 2 items are identical. Yeah. Okay. Yeah, so here we don't need to merge ABD and ACD because they share only prefix of the length 1 instead of the length of 2. But we need K minus 2 first item that should be identical. Okay. Then after we get the all candidate list, generating the candidate, this one, after we generate all the candidate, we